Okay, so where are we? Here we go. So you've had a bit of practice this morning on designing a discrete event simulation and starting to really think about what are the key things you'll need to consider when you're moving from a process map of a real system to then extracting what are the questions that are being asked, what do I need to get out of this model, what are the outputs I'm going to need, and then thinking about, based on that, how do I need to design my model, what aspects do I need to capture? And that's usually going to be a subset of the process map, and usually very often you'll find it's quite a small subset of the real world system. There'll be lots of complexities, as you've just seen, that don't actually need to be included or can be simplified right down in a much simpler way. And actually that design of the model, moving from the process map, capturing the real world system, to then distilling that down and creating the conceptual model. Remember, we talked about the modeling cycle right at the very beginning of this course. That's a big aspect of particularly for discrete event simulation modeling. That will take up a big part of your time. So if anybody that's doing projects using discrete event simulation, don't underestimate the amount of time that will take in terms of getting that conceptual model right. But of course, there will come a time at which you need to actually create the simulation itself. And in order to do that, we're going to show you in this course how to use a piece of software, a package called SimPy. And SimPy is a Python library that basically provides a framework to allow you to pretty easily build discrete event simulations. And the way it does that is it's already set up these concepts of in discrete event simulation. There are entities and they flow through activities and they arrive rates that are defined by inter-arrival times, etc. So we don't have to code all that from scratch. We don't have to tell it. If we were doing it without SimPy, we'd have to create code that explains what an entity is and what an activity is, and create all of that structure. But by using a package like this, we can simply, it already knows about these concepts, and we can then create a discrete event simulation much more easily. So SimPy, I'm not going to go into great detail about it today. You're going to be taught how to use it in the subsequent discrete event simulation sessions, but I am going to just talk to you a little bit about how it works, and I'm going to show you a piece of code written in SimPy so you can see the kind of structure, and I'm going to talk you through it. Now, SimPy is actually built around something in Python called a generator function. So I'm just going to do a little doodle that will help explain this. Okay, so far you've been used to, in Python, the concept of functions. Let's unplug and replug that. Okay, for some reason my tablet doesn't seem to be working. Oh, there we go. Right. So yeah, you've been used to the idea of standard functions, where essentially you define some functions over here. So maybe that's sum up numbers. You did one the other day that was a check whether a number is prime or not. And you define all these functions, and then we said that you sort of trundle along in your main code, and you say, oh, I need to sum up some numbers. I'm going to call the sum function. So you give it some inputs, sum does its thing, and then out the other side, it gives you the outputs, and then you trundle along and say, oh, now I need to check if a number is prime or not. So I'll give it those inputs. The prime checker does its thing, and then it chucks back an output, and we trundle along. So you're all familiar with that now, that idea that you define some functions, then you call on them, and they're kind of single use. You call a function, you give it some inputs, it does its thing, and then it chucks back some outputs. However, there is in Python a different kind of function called a generator function. And a generator function works slightly differently. So with a generator function, we define the function in the same way with a name, and we say all the things that we want it to do, and we pass it some inputs, and it will return some outputs. So in the same way that a normal function would. However, the difference with the generator function is that it retains a state. And what we mean by that is that, so in a typical function, when it's run, once it returns the outputs that it needs, the next time that function is called, it starts again, as though that function had never been run. It runs it fresh every time. With a generator function, it doesn't do that. It remembers where it was, so that the next time it's called, it will pick up exactly where it left off. So here, let's imagine we've got some code that does some various things here, and then at this point, we return something, we return an output. So what happens is then the code trundles back along, and let's say then we call on the function again. And rather than going back to the beginning, what will happen is then when that function is called again, it will then resume from where it left off and carry on through the rest of the function. Now, you might say, that seems a bit weird. Why on earth would we want to do that? Turns out this is actually really useful for modeling. In particular, SimPy is built around this concept. Because if we think about our generator function as being able to do things like generate new entities, acting as a discrete event generator, or going through a process where actually we need to something to happen, so they may wait to see a GP, and then while they're seeing the GP, nothing's going to happen for a while with that patient until they finish seeing the GP. But then when they have finished seeing the GP, then they need to carry on from that point. They're not going to go back around the system from the start every time. So it turns out these things are really useful. So let's have a look at an example of this. So as I say, differs in conventional functions primarily because of this idea that they retain their local states, they can carry on where they left off. So I'm going to show you a piece of code now, a demonstration of a generator function. So in this function, this is an example of a generator function. So here I've got a keep count. All this function is doing is just keeping count of a number. It's just adding 1 to a count. So not a particularly exciting function, but it demonstrates this nicely. So the way we define the generator function is in exactly the same way we define any other function. So here I've used the def keyword, and then I've given it a name, and if I want any inputs, I don't in this case, but I'd put them in the brackets. So all exactly the same as before. Then in our function body, we outline what we want the function to do. So here I'm going to set up a count variable, and I'm going to set that initially to 0. And then I'm going to set up an infinite loop that says to keep doing this indefinitely while the code is running. So we use my while true, and I'm just going to say add 1 to the count. Okay. Now this is all stuff that you would put in any function. The bit that's different and that marks this out as a generator function is that rather than using return to return the count, we use a keyword called yield. Now, yield is like return, but it tells the Python this is a generator function, and therefore, rather than just returning it and then the next time you run this function will go back to the beginning, it says, no, return this, but freeze where you are. Remember where you are, so the next time I call you, I want you to carry on from exactly this point. Okay, so what should happen in this case is if we ran this function, then we should start with a count of 0, and then we'd start in our infinite loop. We'd add 1 to the count, so count would now become 1. We'd then return that count, but because we're going to, so the number of 1 would be returned. But because this is a generator function, when we then resume, it'll resume from this point. So the next thing it will do is go back around the while loop, and it'll add another 1 to the count. So count will now be 2, and it will return 2. And then the next time around, it will go around the loop again, it'll return 3. So it's going to keep freezing and unfreezing. And every time it unfreezes, it's going to unfreeze at the point at which it froze, which is the yield. And it's going to go carry on, which in this case is just going to tell it to go around the while loop again. Now, the way we call a generator function is a little bit different as well. So you're used to normal functions, you call that function, and then you store the output, the things that are returned, into a variable value. Here it's a little bit different. It's more of an object-oriented style. So we create an instance of the generator function. So here I'm going to call the keep count generator I defined above, and I'm going to create an instance of that, and I'm going to call it my generator. So that hasn't called the function. That all that's done is said I've now got a new instance of this generator function called my generator. And you might think, why do you have to do it like that? But think about this. If you've got a generator function, which essentially remembers where it is each time, well, we may want to call that function separately for lots of different things, and we want to remember where each of those separate functions are at any one time. So if we think about patients, we want the generator function representing one patient to remember that it's currently seeing the doctor, and when we return to it, it's going to then move to the next step. But then we want a separate generator function for another patient that says they're currently with the receptionist. We need to keep a track of all of these different instances because they'll be at different points. So we're going to create an instance here called my generator, and then what I can do, I can call that function, call the generator function, and I can treat it as an iterator. So an iterator is just an element like a list, for example. You've seen lots of examples of iterators. That's an iterable object, but an iterator like a for loop or a while loop. We can use something called the next keyword to say run this iterator again until you pass control back. And in this case, for a generator function, that says run the generator function until you pass something back, and then you're essentially freezing in place. So down here, I've put print and then next my generator. So that means move to the next element of the iterator. In other words, run this function until you return something, at which point you'll freeze in place. And then do that again, and do that again, and do that again. Now, I've done that 5 times here. So I'm basically telling the generator function, I'm calling that 5 times. Now, I could have put all that in a for loop, but I'm deliberately split out this. So you can see that I'm calling that 5 times, and I'm just calling the next keyword on that generator. So let's now look. If I were to run this, we can see over here that it's outputted the numbers. Just ignore the bottom ones for a minute. It's outputted the numbers 1, 2, 3, 4, and 5. Because the first time it was called in this line here, it will run the function from the start. It sets count to 0, and then it adds 1 to the count, and then it returns that count, but it freezes in place. So it's printed the returned value of 1. When we call it again here, it resumes from this point, from the point at which we left it. So rather than going back and saying count equals 0 again, we're starting from here. So we're going to go back around the while loop, we add 1 to count, so it'll then return a count of 2, and so on. And then the next time it'll return a count of 3, etc., etc. That function would not work if you had it as a standard function rather than a generator function. And to demonstrate that, I've put it here. I've done exactly the same thing, but in a normal conventional function, called this one conventional keep count. Exactly the same. I've got a count set to 0 as the first step, and then I've got an infinite loop that just says add 1 to the count and then return that value. But by using return, I declare this is a conventional function, not a generator function. And if I do that, if I call that function, which I have to do slightly differently and the way you're used to, and then I print that value, each time it's just going to print a value of 1. Because each time you call that function, it'll set count to 0, and then it'll add 1 to 0, and it will return 1. Because every time you count that, it's going to go back to the start. So that would be a conventional function versus the generator function, where it picks up from exactly where it left off. So this is really useful, as I say, for doing discrete event simulation, and SimPy is built around this concept. So let's have a look at a very simple SimPy model before we break for lunch. So let's just take one little aspect of our model that we've just been talking about. So here I said that one of the things I wanted for my model was a generator for people arriving for the weight loss consultation, who then queue for the weight loss consultation activity, which needs a nurse, and then they exit via a sync. So we've got inter-arrival times in terms of the arrivals waiting for the weight loss consultation. Our entities are patients, and the activity times are the time spent in the weight loss consultation. So I'm just going to talk you very quickly through this piece of code, how you would develop that model in SimPy. Now, I'm not going to go into detail about this. I just want you to, and I don't expect you to be able to write a SimPy model from this. You're going to get practice now. We're going to show you how to do that in the subsequent discrete event simulation sessions. But I just want to talk you through the basics of how we would do this. So as normal, we would import the libraries we want. So I'm going to use the random library here because I'm going to be using distributions. But I also need to import SimPy as well. So what we do is we set up, the first thing I'm going to do is set up a generator function, the things we've just talked about, that will represent my patient generator. So this thing, the thing that's going to bring in new patients into the weight loss consultation. Now, we pass into that generator function the things that we're going to need, the things that generator is going to need. And the first thing it'll always need is the environment, the SimPy environment, the model environment. Don't worry too much about that at the moment, as I will explain more about that in the subsequent sessions. But basically, you need an environment in which your simulation is going to run. We're also going to need to pass it, though, information it's going to need about the inter-arrival time. So we're going to need to pass in the inter-arrival time, the amount of time between patients being generated, because this is going to generate our patients, as well as the mean consultation time, because we're going to need that when we set off the patients on their journey. And we're going to need to pass in the resource of a nurse. So in this generator function, I'm just going to set up a patient ID variable, and I'm just going to use that to give each patient a unique identifier. So much in the same way I used the count on the generator function before, this will set, the first time it's called, it will set it to 0, but then every subsequent time, every subsequent patient that's generated will then have an incremented patient ID. And then I'm going to use my infinite loop here to say, keep doing this indefinitely while the program is running. So the first thing you do is you create an instance of the activity generator, which I'm going to come down in a minute. That's another generator function that's called, that basically says, this is the journey that the patient will take through our system. And into that, I'm going to need to pass the environment. I'll also need to pass the mean consultation time, because that's where the patient is going to consult with the nurse. I'm going to need to pass the nurse, because we're going to need a nurse resource. And I'm going to pass in the patient ID that I've created as part of this generator function. So once I've started that thing running, I'm then going to tell the simulation environment to run that activity generator function for this patient. So I'm going to say, create an instance of it and then start it running. So imagine it as you've got one generator that's you start running at the start, which starts generating your patients. They're coming into being in the system. And then each time a patient comes into being, that patient then has another generator that starts their journey through the system. Okay. So we start that up running, and then the next thing we need to do is, in terms of generating new patients, is to say, okay, well, how long until the next patient comes into the system? And we're going to use an exponential distribution here. So I'm going to use the expovariate method of the random library, which you had practice using last week. And I'm going to say, yeah, the mean is, so lambda, remember, is 1 over the mean. So I'm just going to say it's 1 over the mean that I passed in. So if the mean inter-arrival time was 5 minutes, then that will sample the time that the next patient will arrive with a mean of 5 minutes, but it will sample it from an exponential distribution, as you have practiced doing last week. Once it's worked out when the next patient is going to arrive, it will then use a timeout on the environment and use the yield keyword. So it'll pass control back to the SimPy simulation environment, but using yield, it says this is a generator function, so freeze exactly where you are. So that's this generator function here, which is basically creating new patients, will then freeze for the amount of time that we've sampled to say when's the next patient. So if we sample that the next patient's going to arrive in 6 minutes, it will freeze for that amount of time, a simulated time. So then when it unfreezes, when 6 minutes of simulated time has elapsed and we're ready for a new patient to come into the system, then it will resume from that point because it's a generator function. So it will start from here and say, okay, right, where was I? Right, the next thing I'm going to do then is I'm going to increment the patient ID by 1, ready for my next patient. So the first patient that was generated had an ID of 0, and then the next one that comes in will have an ID of 1. And then it'll carry on from here. So it'll go back around the while loop and it'll say, right, okay, I'm going to create a new generator for the activities for this patient, and I'm going to set that running. And then I'm going to work out how long it is until the next patient comes in. I'm going to sample that from an exponential distribution, and then I'm going to freeze in place until I'm ready to generate the next patient coming into the system. So that's basically what this generator function is doing. It's just saying, keep creating new patients and set them on their merry way. That's basically what it's doing. And each time it freezes in place until it's ready to generate the next patient. And then we have a separate generator function here that's the one that we're creating up here. So for each patient that came in, we said we'll create a generator function to set them on their merry way, and that's the function that we're setting off up in the other in this function here. And this basically, the best way to think about this is represents the patient's journey. So this says, right now for this patient that I've generated, send them on their journey through this system. So the journey through this system is very simple. They come in, they wait for a nurse, they get a consultation about weight loss, and then they leave. Okay, so it's a very simple journey. So into this function, we've already said we're going to need to pass the environment, the simulation environment. We'll need to pass the average time a consultation takes, because we need to sample that. We're going to need to pass the nurse, because we need a nurse, and the patient ID that they were given in this function. So what we can then do, the first thing we can then do is to say, okay, when this starts up, the first thing they're going to do in that system is wait for a nurse. They're going to join the queue for a nurse. Maybe there's no queue at all, but they're still going to join a queue, even if it's a queue, they're queuing for 0 minutes. So we can record the time that they entered that queue by using the environment.now keyword, which basically says, give me the time in the simulation now. So that when that starts running, we can say, okay, the patient arrived now. Then what we do, now do you remember, I can't remember if it was last week or the week before, that we started talking about, I think it was the week before, we started talking about the with statement when we talked about files. And we said we can use the with command to say, keep this file open whilst I do all this, but then automatically close it. The with command we can use here to essentially say, give me a nurse, and then do all of this with a nurse. And then once you've done all that, you can release the nurse. Because essentially what you're doing in the simulation is you're saying, I need a nurse to undertake this activity. I need the nurse. I can't do anything with this process until the nurse is available. Once the nurse is available, I will then be able to do all of these things, and then the nurse can be released. Okay, so this with nurse, which is the resource that we've passed in, dot request as rec, that basically means request a nurse and do all of these things. And then the first thing it will do is use a yield statement to say yield that request. In other words, freeze this function in place until a nurse is available. So this function then won't, that will then freeze because it's a generator function, and it will wait until a nurse is available. SimPy will do that for you. SimPy will essentially say, once a nurse is available, we will give you the nurse. So once that happens, the function will become unfrozen, because this generator function will resume from exactly this point. So it will then carry on, and we can then record the time that it is now in the simulation. And that, of course, represents the simulation, the queuing time. If they started queuing at time 0, up here, and then they had to wait 5 minutes for a nurse, and so the simulation time is now 5, we can record that and then calculate very easily the time they were spent queuing. It's just the difference between the time now when they've got the nurse because they've come back in versus the time when they first came into this function. Once the patient's got the nurse, then all we need to do is to sample how long they're going to spend with the nurse, in this case, the consultation time. So remember, we passed in the average. We're going to sample from an exponential distribution. So we put in 1 over the mean. That becomes the consultation time, and then just like we did for the generator function up above, which was generating new patients and then waiting for the amount of time before the next patient came in, here we're doing the same thing, but we're saying now freeze this function in place until the consultation has finished. And by doing that, by freezing that function in place, we're still within the with statement. So that nurse is going to be held until this patient has finished with them. So you're saying, basically give me a nurse, freeze in place until a nurse is available. Then once a nurse is available, work out how long you're going to spend with the nurse, and then freeze this function until you've finished with the nurse. And by doing that, you're holding the nurse. So if you've only got one nurse, nobody else can use that nurse whilst the patient is with them. And then we can put in a little message here that says the patient then finished with the nurse at whatever the time is now. So all we need to do outside of these two generator functions, remember, one is basically spewing new patients into the system, and the other is describing their journey throughout that system, each patient's journey. We simply set everything up. So we say we set up a new SimPy environment, and we store that as env. We set up a new SimPy resource, and remember I said the beauty of using something like SimPy is that we don't have to write what a resource is or what an activity is. SimPy knows all this. SimPy's got a concept of a resource. It's got a class called resource. So we can say, yeah, nurse is a resource. You know what to do those things. And it's going to live in this environment, and it's going to have a capacity of 1. So in this model, we've just got 1 nurse. That means that we could very easily say, okay, I've got 10 nurses now. There we go. I've changed it. I've now got 10 nurses in my model. It allows us to really easily play with capacity. I'm going to set up my times. So I need an inter-arrival time, an average inter-arrival time. I'll set that to 5 minutes. And I'm going to set my mean consultation time to 6 minutes. So we would expect from running this there to be a queue. Because if you think about that, on average, patients are arriving every 5 minutes, but on average, they're spending about 6 minutes with the nurse. So we would expect there to be a little bit of a queue forming, because on average, patients are arriving a minute quicker than they're able to be seen by the nurse. So it's taking a minute longer on average. So we expect a queue to start building. Once we've done that, we just fire up our patient generator function, the one at the top, which starts spewing out patients. We set that running and then tell the simulation to run for an amount of time. So my time units here, I'm going to use them to represent minutes. So run for 120 minutes, so 2 hours basically. So if I were to run that, we can see, I don't know how well you'll be able to see this, but I encourage you to run this yourself as well. You'll be able to see in this case, patient 0 came in first. They entered the queue at time 0. They left the queue at time 0 because there was nobody in front of them. So they queued for 0 minutes, and they finished with the nurse half a minute later. Okay, so they're really quick with the nurse. Exceptionally quick, actually. Then patient 1 entered the queue at time 0.889. They left the queue straight away because there was nobody in the queue ahead of them. And so they spent much longer with the nurse. They didn't leave until the nearly 10-minute mark. Patient 2, fortunately, didn't come in until just after, so they weren't queuing either. And they finished at time 12, etc., etc. But you'll see as you start scrolling down, and obviously it'll differ for each run. So if I look at patient 3 here, patient 4 entered the queue at 21.65. Patient 3 was still with the nurse, so they had to wait. So patient 4 had to wait for 3.5 minutes before they were then able to see the nurse, which then started to cause a bit of a queue. And as you scroll down, you'll see generally people will start queuing more and more, which is what we'd expect, because people are coming in a little bit more frequently, a little bit more quickly than the nurse can get through them. So we'd expect to see a queue building. That was a very, very quick whistle-stop tour of a SimPy model, and I absolutely do not expect you to be able to write a SimPy model from that. But it's just to get you familiar with the basic concepts. So when we go into the next session of the discrete event simulation module a little later in November, you'll start to see how these models are built. And basically, it all boils down to this. you've got a generator function that creates your new patients or new entities coming into the system, and then every time a new entity comes into the system, you call a second generator function, and that generator function then describes their journey through the system. And principally, that's a series of grabbing a resource and holding it for an amount of time and then releasing it, and then grabbing another resource, holding it for an amount of time, and then releasing it. And it's all built around the concept of generator functions. So it's worth getting to understand how those kinds of functions work. Now, in the first session, the next session, I should say, so session 5B of discrete event simulation, we will go through and you'll get a chance to build one of these things, and we'll build that up gradually. And then in the session 5C, we'll show you how you can then do it in an object-oriented way. So using the principles of object orientation, you can build a object-oriented version of a SimPy model, which is actually, although it's a little bit more difficult, initially, you'll find it much more elegant, because you may well have already thought, this looks a bit messy that I'm having to keep passing around my environment and my nurses and all my resources. And you're right, because this way of doing it, every time you're passing into your generator function here, you've also got to pass it all the things that generator function is then going to need to pass on again to another generator function over here. That's fine for a very simple model, but the second you get into more complex models, you're going to be passing huge amounts of stuff all over the place. The object-oriented method means you don't have to do that. You can create an instance of a patient, and a patient follows this course of things, and it's a much neater way of being able to do that. So what I'd advise as revising after the session is to go back and have a look at the notes on generator functions, and then to run this function. Hopefully you've all got SimPy installed now. Run this simple simpy.py file and have a read back through it. I've put lots of comments in explaining how this works, and just get your head around the basics of how this thing is working. You don't need to fully understand enough to write it yet, but just see if you can broadly understand what it's doing and how this thing works, and run it and have a look at the output and see what's happening. Play around with putting another nurse in, see what happens. Change the inter-arrival times, change the amount of time they're spending with a nurse, and see what happens to those results. Okay, I think it's pretty much time for lunch. Any questions before we break?
Sorry, hello?
Hello.
Hi, I just wanted to say that it's quite easy for all of us to quantify the consultation time or the call time and these sorts of times, because of these are all recorded on our systems.
Mm-hmm.
But the wrap-up time after a consultation is finished or a call is finished is not so easy
Mm-hmm.
to quantify. So how do you sort of work out that wrap-up time, that time where they're finishing off the notes for a session? How are you managing to sort of put that into your model?
Okay, so you'd need to include it in some way, because you'd need to, if that's blocking your resource, which obviously it would be,
Yes.
in that
Yes.
instance, then you'd need to include that. So if you haven't got, the best option is obviously to collect some data around that, to try and get that. And if that's not possible, then essentially all you can do is to put in an estimate. You'd want to put in some variability around that estimate.
Yeah.
So you might say, okay, well, we'll imagine it's exponentially distributed and it's about 3 minutes on average. But then what you'll probably want to do is to do some sensitivity analysis around that, to say, okay, well, if that's massively wrong, is that going to be a problem? Is that going to throw out, if actually I've underestimated by half the amount of time that's taking, how does that impact my results?
Yes.
So you can explore that as well. Yeah, dealing with data that is not routinely collected is always tricky. The best solution is always to try and collect even a sample of data to give you some idea, if you can, for the purposes of the model. But if that's not possible, to at least gauge some sort of expert opinion, and then put in a bit of variability around that.
And what would your sort of minimum sample size be for something like that?
That varies hugely depending on the context. So you want, it also depends on how variable it is in reality. So if actually a lot of wrap-up times are very similar, then you will only need a relatively small sample to get a represent. So you probably want to start off looking at as you're collecting your data to get a judge on how variable is this? Is this all over the place? Is it that some people are taking 3 minutes, some people are taking 20 minutes, some people are taking 1 minute? If that's all over the place, you're probably going to need a larger sample to get a better handle on where that is. So it's a bit of an art form.
Yeah, no, that's great. Thank you.
No worries. Any other questions? No? Great. Okay, I probably I'll shut up now. It'd be good to give you a bit of a decent break. I'm conscious I don't want to cut too much into your lunch break. Kerry, would it be a massive problem if we started at 1:40, for example, for you?
Hello.
Hello.
Well, I prefer to get started at 1:30 if
okay.
Because it's quite a tight schedule. I'm trying to squeeze a lot in to yeah, so it would be best actually if we could keep to 1:30. Sorry about that.
No worries,
that's
okay.
45 minutes.
Yeah, okay, yeah, no worries at all. So yeah, we'll resume at 1:30. Remember, you're going to be with Kerry this afternoon, looking at QGIS, so you'll get some really nice training on that software. Remember the login details. Kerry will be hosting this, so they're different, so make sure you do look, if you haven't already, in Slack. Kerry has put the link under the Module 6 channel, so you'll be able to see all the details in there. Fantastic. Go and have a break, have some lunch, and we'll see you back for Kerry's session at 1:30. Great. Thanks, everyone.